Welcome to attend our another energy system seminar. And today we have Emil from the Department of Electric Energy at NTNU to present his recent work on power system decarbonization under risk aversion and incomplete markets. Just a bit of information about Emil. He's a PhD candidate at the Department of Electric Energy and also a research affiliate at MIT. And he has also worked as analyst in the private sector, focusing on climate policy issues. So the floor is yours, please.
Thanks, Hongyu, and thank you for joining in person and online. I'm excited to present to you a part of my PhD, which is on the implications of investment risk for the clean energy transition broadly. This paper here that I'll be talking about is to a large degree a methodological work. So I will be showing you how we model risk in energy system models. And then I'll talk about some of the early stage policy insights that we get from this modeling in this paper. This work is available as a working paper already, and we are currently getting it through peer review as well. The problem that motivates this work is that tackling climate change is a problem of investment. So in order for governments to achieve their climate goals, they have to both reallocate existing investments from fossil fuels toward clean energy, like renewables, like storage, and increase total energy system investment. So that leads us to the question, what drives investment decisions? And our focus is on power markets that are liberalized. So we're talking about private firms and how do they make investments in generation and storage. So for companies like this, if you talk to them or if you read finance textbooks, you learn that in first principle terms, there are two things that matter for investment. One is profitability, and the other is risk exposure. Risk exposure is something that's not often captured in energy system modeling, and that is our focus. To manage risk, investors rely on long-term contracts. An example of this is power purchase agreements, which are common here in the Nordics. We use them in the US. They're also used throughout Europe to a varying extent. And if you talk to wind and solar investors in particular at the utility scale, they'll tell you that they will almost never invest unless they can sign a long-term contract that guarantees revenues and reduces risk. One problem, however, with electricity markets that are liberalized is that these long-term markets are what we would call incomplete. More specifically, contracts for long-term contracts are generally not very liquid. So if you look at the markets, there's not a lot of liquid trading, and also they're missing entirely in many cases. So they're forward markets, for example, don't provide contracts that are 10, 15, 20 years out that investors are typically looking for. So there is a limited ability for investors to hedge risk. This leads to what's called in the literature and the industry, the missing market problem. That's not to be confused with the missing money problem that many of us are maybe more familiar with in power systems. So this is a whole different market failure that characterizes liberalized power markets. And we wanted to know what is the impact of the risk that investors face as a result of this problem for power system decarbonization. So we asked two questions in particular. Number one is, how does the risk exposure that investors face impact, hey Magnus, hello. How does the risk exposure of investors impact power system decarbonization relative to ignoring risk? So this is a methodological question. It asks, if we take one approach that is more traditional that ignores risk, how does that bias our results compared to if we account for risk? The second question is more of a policy question. And here we ask, how does the missing market problem affect power system decarbonization? So we construct 3 models to answer these questions. If we look at question number 1, we address it by constructing these 2 models and then comparing them, and that helps us answer the question. So first, we start with a traditional energy system model that ignores risk. This is also called a risk-neutral approach. So this is we'll talk more about what this is, but this is, for example, the Empire model that we have here at NTNU. Our main contribution is to build a model of generation expansion that actually captures both the risk aversion of market participants and this incompleteness of markets. So by comparing them, we can say methodologically, what are we missing when we are ignoring risk? To our second question, we answer it by comparing the power system with missing markets to a power system that has complete long-term markets. So this is the theoretical optimal power system that we should have. So by comparing these 2, we can say, how does the missing market problem distort markets and the clean energy transition in general? So we call this model a risk-neutral case. I'll refer to the main experiment as a missing market case, and the theoretical optimal is the complete market case. How do we model this? So if you're trying to model a risk-neutral power system expansion problem, you use stochastic optimization. We all do that. So this is the traditional approach to modeling power system investment under uncertainty. On the slightly more sophisticated, we can represent risk under complete markets if we include risk aversion in our optimization modeling. So here we can model, what would be the perfect outcome of a perfectly planned system where all markets are well functioning. The middle model is more challenging, and this is our main methodological contribution, where we the only way to model this, or at least our way of modeling this, is as a stochastic risk-averse equilibrium problem. So it's no longer an optimization problem, but equilibrium problem. So to give you some intuition of how do we model this absence of long-term markets using equilibrium. So the key idea is that we're disaggregating the generation expansion problem. So we start with a risk-averse optimization problem, and that's essentially representing the decisions of a central planner that's planning the power system under risk. We recognize that this model implicitly assumes that any market players that are being represented by this model are trading risk perfectly. So there are complete markets for complete long-term markets here. The way to model missing markets is by disaggregating the generation expansion problem into an equilibrium between individual market agents. So this disaggregation is how we represent the fact that these agents might or might not be able to trade long-term contracts and share risk. So how do we do that? I won't show math, but I will just show kind of the intuition behind the optimization and equilibrium approaches. So as I mentioned, we disaggregate the problems of different market agents. And we do it like this. So first we formulate a risk-averse investors optimization problem. And that's to maximize profit subject certain risk preferences. And we can talk about how we model those. So this is a linear program talking about, and then we model a system operator's problem, which is to minimize total dispatch cost, subject to all of the engineering and economic constraints that we typically have in a energy system model. So this is the first problem on the left, maximizes profit and calculates optimal investment decisions of these investors. And then this problem calculates the optimal dispatch of the system in any given scenario. When you take them together, if you ignore risk and take them together, that's equivalent to the traditional generation expansion problem. So even though it might look strange and fancy, it's consistent with our canonical approaches. The way we actually solve this is by combining these two problems together into an equilibrium problem. So that's why our model is an equilibrium model. And the way we do that, there are many ways to do that, and we tried them all, or most of them. But computationally, what we found to be very promising is to use a primal dual approach that formulates each of these optimization problems as a primal dual problem, which involve taking the strong duality condition and primal and dual constraints of each of the optimization problems. And ask me after if you want to talk more about that. Here I wanted to kind of summarize our methodological work, how we actually build this equilibrium model and make it solvable. So as I said, we have an equilibrium risk-averse generation expansion model that we're building. The first step, as I already introduced, is to formulate the primal dual equilibrium problem. So this is some algebra and math and operations research theory. The second step is we have certain non-convex terms in our problem that we come up with an exact reformulation for. So we have some mathematical proofs in the paper of why this works, but we can replace certain non-convex terms with integer terms, which makes our problem tractable. And at the end, our problem is an MIQCP, mixed integer quadratically constrained program that can be solved with off-the-shelf solvers pretty tractably, although we are still incurring a computational cost relative to using a generation expansion optimization model. But we still think we can solve some very meaningful problems with our model. And that's partially because, so number 3, we come up with this representative investor formulation where we use only one agent to represent the decision-making of all investors that might be in the market. We also showed that this is equivalent to having individual investors. This is just a convenient way to have a lot more computational efficiency. By the way, we borrow this idea from macroeconomics where people use these representative agents. I guess I wanted to say conceptually that even though we have one investor, there's no market power in our model. So we have a perfectly competitive market. So again, consistent with traditional approaches. Finally, we come up with the numerical robustness procedure, which allows us to test for multiple equilibria, which is one of the main problems with this kind of modeling is that the model can give you multiple solutions, each of which theoretically seems correct. And you want to know if that's the case, and you want to know what those solutions are. So we can address that with our approach. And the tradition, we compare our approach to the traditional way of modeling equilibrium problems, which is with the path solver, and our method performs significantly better. The path solver in particular fails to give a solution in a problem as big as ours. So we haven't conducted exhaustive tests, but in the tests that we did conduct, our model actually makes the problem solvable as opposed to the traditional approach. So I'm going to now get into the analysis that we did and the results that we got. We designed an experiment where we have a power system with 4 technologies that are, I think, a representative of technologies we'll see in the future. So there's gas, wind, solar, and batteries. I guess about the batteries, one thing is that so our model does have time linking constraints. So all of that computational complexity we can capture. We use representative periods to reduce the scale of our problem, but we still solve power system with 30 representative days, 720 time steps. We also solve bigger problems with 16 representative weeks at an hourly resolution. So we can solve models with hundreds of thousands of variables, which is still smaller than state-of-the-art optimization problems, but still, I would say, large enough that we can capture renewable variability, storage, and important things like that. In our experiments, we model two uncertainties. We assume that demand is uncertain, and demand can vary by plus or minus 25%. So this represents uncertainty in electrification, hydrogen electrolysis demand, etc. And we assume the gas price is also uncertain with plus or minus 25% variation. Great. So now we can move on to the results. And I'll show you some of the main results, and I'll have to leave a lot out for the sake of time. But going back to our first research question, which was methodologically, what happens when we ignore risk and what happens when we represent risk? That's what I'm showing here. So the left set of bars is the capacity mix in the power system in 2050 if we ignore risk. So this is if we use a traditional model that assumes that investors are risk neutral. And we have some gas, a lot of wind, a lot of solar batteries. On the right is our main model where we take into account risk and the fact that markets are incomplete. And so the difference is that storage, solar, and wind investment is less, and gas investment is a little bit more. This is not a very important result about gas, but we see that both storage, solar, and wind decline. As a result of this, power system emissions are higher when we account for risk. So that tells us that when we account for risk, we would expect the clean energy transition to be slower than if we ignore risk. So that seems like a pretty important thing to be modeling. In the interest of time, I'll just tease the main drivers behind these results. So there are three drivers here. First of all, each technology has a unique risk exposure that the model captures endogenously. Second of all, each risk exposure changes each technology's costs. And it does that by increasing the cost of capital for each technology. So that happens endogenously in the model. Most previous literature focuses on number two, and they say, well, clean energy investments are more capital intensive, so risk is clearly a big problem for them. And that's where a lot of the literature sort of stops. But our energy system modeling approach allows us to capture both 1 and 3. So I went through 1. Number 3 is, once we know how technology costs change as a result of risk, we want to know then how does this change the actual system outcome? So our model does that. So all these 3 things are driving our results. On to question 2, which is how does the fact that markets are missing impact power system outcomes and decarbonization? So in this bar plot, again, I'm showing the capacity mix. That's one of our main results. Let's ignore the left set of bars. I already showed you, that's the risk neutral. So the middle bar here is our main model where markets are missing. And the right set of bars is the theoretical optimal where markets are complete. So you can interpret the right set of bars as the world that should be, and the left set of bars as something representing the world as it is. There are a lot of simplifications behind this, but our goal is to directionally say what the impact of some of the real world risk, real world risk exposures, actually what their impact is. Okay, so comparing the left set of bars to the right, we see that once again, actually, wind, solar, and battery investments are less when we have missing markets compared to what we should have if we plan the system optimally. As a result of this, emissions are also higher when markets are missing. So this tells us that the missing market problem is slowing down decarbonization, and also leading to suboptimally low renewable and storage capacity. So ideally, we should have more renewable and storage capacity, as shown on the right, but the lack of long-term contracts results in us having less. That's what this is showing. So the 4 takeaways that I'd like to kind of highlight are here. Number 1 relates to our first research question, which is kind of a methodological point that omitting risk exposure can bias energy system model results. In our particular case, we saw that ignoring risk exposure leads us to expect more clean energy investments, and then we actually see if we model risk. Whether that's a generalizable result is it's not necessarily a generalizable result because we are conducting preliminary analysis here, but it seems like an important area for future work. So the last 3 points relate to our second research question, and they're more of a policy discussion. So number 2, as we saw in our results, missing long-term markets can increase CO2 emissions. So that's because clean energy investors face risk, and that risk is more than is societally optimal for them to face. Number 3, then following from number 2, long-term markets can bring climate benefits by decreasing risk for clean energy investors and therefore decreasing emissions in the future. And they can also bring economic benefits because what we're talking about when we say markets are incomplete is that's a market failure that not only has these climate implications, but it actually means we're in a suboptimal society, in a suboptimal future. So this is kind of I think, optimistic, point that we can both tackle climate change and actually improve economic outcomes at the same time if we have more long-term markets. And finally, long-term markets are important not only for generation, which has been the focus of previous literature and the focus of a lot of our discussions in the field, but also for storage. So I think we should start thinking about some kind of long-term contracting for storage and more generally flexibility resources, because in our work, we see that they face significant risks, and those risks significantly impact their investments compared to what is optimal. Thank you very much.